Greetings, salutations, all those nice things. This is lesson 10.5, where we look at sine graphs of higher order polynomial functions. For a bit of a recap, rewind. We looked at drawing sine diagrams for quadratics specifically. And with quadratics, it did require us to be able to factor what we had, because by factoring, we could find the zeros of the related function. And the zeros are the critical values because it's at those zeros that we could switch from positive to negative. Granted, it doesn't always happen. Sometimes you go from negative to negative, just in that case if the vertex is on the x-axis. Or we could go with a negative, positive, negative vibe. But we're always trying to figure out what's happening in each of those intervals. And with quadratics, it was kind of nice because we could just picture the quadratic and decide if it was opening upward or opening downward, make decisions on the sine diagram that way. We're going to look at these higher order polynomial functions in this form. So these ones are already factored for us. We don't have to worry about the factoring. That's a next year problem for us. And from this factored form, we can again find the zeros of the function because those will be our critical values. And from that, we are going to make the sine diagram. Things kick off the same way. We know that our critical values are -2, 1, and 5, because that's what makes each one of these factors equal to 0. In the plotting of our sine diagram, then, we'll have this extra special number line with those critical values on here in numerical order. We know that those are the values of x, and on top we're going to say things about f of x. And for sure we know that at those x values, f of x is 0. That's why we chose them. That's the whole point of choosing them. Because at those x-intercepts, we could potentially cross over the x-axis. We could go from negative to positive, positive to negative. But we've got a bunch of intervals. There's this whole zone over on the left. That's everything that happens before x is -2. So when x is -3 or -4 or -5, maybe even -1,000,000. That's what's happening there. In the middle, or this first middle interval, we've got all the values from -2 to 1. Those are the x values, and f of x will have its own values. Then there's all the values from 1 to 5. So it could be 1.1 or even 1.001 or 2 or 3 or 4 or 4.9. Lots of options there. And then everything on the very right side, everything that's more than 5. This could be 5.1, could be 6, 7, 8, could be 100. But those are the x values we're dealing with. So for this first interval, let's find the sine. And we're going to use kind of a slower method right now with test values. And we'll see how that translates to us kind of getting a faster method. But for this interval, we can choose any x value in this interval as our test value. And we'll put it in here just to see what sign we get. So we can choose -3, -4, but anything less than -2. For funsies, I'm going to choose, I don't know, -10. That seems like a good number. I'm going to plug that in for x in each one of these. If x is -10, x plus 2 is -8, so that's negative. If x is -10, x minus 1 is -11, and when we cube that, we get something negative. And when x is -10, x minus 5 is -15, which is negative. And this whole product of x plus 2 times x minus 1 cubed times x minus 5 will be negative times negative times negative. And the product of three negative numbers is itself negative. So that's that first interval done. Looking at the second one, we need some number from -2 to 1. Not those endpoint values themselves, not -2, not 1, but something in between. And if I have the chance to select 0, I usually go for it. So I'm going to select 0. This is the number we're working with. That's what we're going to plug in to each of these factors. So when x is 0, x plus 2 is 2, which makes that one positive. When x is 0, x minus 1 is negative 1, and then when you cube it, it's still negative. So this one stays same. And when x is 0, x minus 5 is negative, so that also stays same. And the product of each one of these factors is positive times negative times negative. And the product of a positive number and two negative numbers is positive. Where is blue? Positive. So we continue doing this with the other intervals. If I plug in this particular value, this value in that particular zone from 1 to 5, maybe I'll choose 3. 3 sounds like a good number. 3 plus 2 is positive. 3 minus 1 is positive, and when you cube it, still positive. And 3 minus 5 is negative. So we're looking at a positive times a negative, which is overall negative. And finally, the last interval, again, we can choose any x value we want that's in this zone. I'm going to choose 100 because I can. Pow, pow. 100 plus 2 is positive. 100 minus 1 is positive, and when we cube it, still positive. And 100 minus 5 is also positive. This one changed. And we've then got the product of 3 positive numbers, which is positive. That is the sign diagram for this particular function f of x. And we got it by plugging in some selected test values from each one of these 4 intervals to test out what the signs of each of the factors would be in each case to get the sign of the overall function. It's cool stuff. It also looks pretty neat. It looks almost like it just goes negative, positive, negative, positive. Wow, that's really wicked. I wonder if they all do that. Well, it's time for you to investigate. Try examples B and C. See what you notice. So pause the video for 5 whole minutes and then resume. Wow, that was a great pause. I hope you finished lots of examples, and by lots I mean 2. I'm gonna rip through this one. My critical values here are 4 and -1 and 9 and -8. So on my sign diagram, this beautiful number line, we'll have all 4 of those options: -8, -1, 4, and 9. Those are my x values for which I'm finding information about g of x. And of course, at those values, g of x itself is 0. I'm going to test out this first interval. I'll try a number like -10, sure. 4 minus, that's an eraser. 4 minus -10 is 4 plus 10, so that's positive. -10 plus 1 is negative, but then squared, that's positive. -10 minus 9 is negative, and -10 plus 8 is negative. So that whole region is positive. Positive times negative gets you a positive overall. Cool. Next region, somewhere between -8 and -1. I don't know. Let's go -5. 4 minus x in that case is 9, so that's positive. -5 plus 1 is negative, but getting squared, so positive. -5 minus 9 is, what is that these days? Yeah, that's negative. And -5 plus 8 is positive. Ooh. So that one changed. The rest stayed same. Interesting. But that one changed. And now we've got the product of 3 positives and a negative. So that whole region is negative. Okay, so we got the alternating thing happening, just like we had in the previous example. Maybe that's going to continue. Maybe we're just going to keep going with that. I don't know. Let's find out. Let's plug a number from this region. When x is somewhere between -1 and 4, I'm going to go with 0. Gosh, I love 0. In that case, 4 minus x is positive. X plus 1 is positive. Squaring it, still positive. X minus 9 in that case is negative. And x plus 8 is positive. I didn't change any of these signs in this case. What a mystery. But in any case, the sign of that whole region is negative. And then moving onward, plugging in, 5. 4 minus 5 is, that's negative now. Boop. 5 plus 1 is positive, squared, still positive. 5 minus 9 is still negative, and 5 plus 8 is still positive. So that whole region, negative times positive times negative times positive, that's positive. And then finally something more than 9. Sure, 100. 4 minus 100 is negative. 100 plus 1 is positive. Square it, still positive. 100 minus 9, that one changes. Now that one's positive. And 100 plus 8 is also positive. So the whole product here is negative. And this is the sign diagram for g of x. If you want, you can plug this whole thing into Desmos and see what you get for the graph. And you'll see that y does change from positive to negative, negative, positive in certain spots. And for some reason, stays negative across this -1. That's so weird. Take a look at what we've done so far. See if you can kind of conjecture where the sign will switch and where it won't switch. So it switched over this 8 from positive to negative. It switched over this 4 from negative to positive. But over this -1, it did not switch. It went from negative to negative. Why did it not change there? These are the mysteries. Make a guess in your head brain, and then see if that applies with this last example, which you also did when you paused the video, all that jazz. So critical values here are 1 and -4. Whoop. So x versus h of x. Remembering we're putting these on our sign diagram in numerical order because we're not monsters. And testing things. All right, I'm going to test something here. Let's let x be -10. That seems to be a solid go-to. -10 minus 1 is negative, but a negative to the power of 4 is positive. And -10 plus 4 is negative. A negative to the power of 5 is negative. So that region is overall negative. Next up, something between -4 and 1. I'm going to select my favorite 0. 0 minus 1 is negative, but that to the power of 4 is positive. Okay. 0 plus 4 is positive. That to the power of 5 is positive. So that product is positive. It did switch when we passed over x equals -4. Okay. Well, let's switch back. Let's check. So something where x is more than 1. Let's let x equal, 10. Now this is the number I'm putting in for x. 10 minus 1 is positive, and positive to the power of 4, also positive, so that stays same. 10 plus 4 is positive, and a positive number to the power of 5, also positive, so that also stayed same. Crazy. And we still have positive times positive, which gets us a total product that is positive. So we see changes sometimes, but not at others. And the key kind of comes down to the exponent we see on a particular factor. Something that's to the power of 4, similar with our quadratics that had a power of 2, they can never be negative. And anytime you have an even exponent on a factor, you know that factor will never be able to be negative. But if you see an odd exponent on a factor, then the value of that whole expression could be positive or it could be negative, all depending on what's plugged in there. And it will always, that switch will happen as we cross over the x value that causes that particular critical value. So our shortcut will be to do one test. We'll do one test value to get a seed going in for our very first spot. And then once we do that, we're going to take a look at the exponent for each particular factor to determine whether the sign switches. And if it's an odd exponent, we'll switch like we see from this negative to positive. And where this 1 had an even exponent, that one had us stay same. If we look back at example B, we notice that as well. The 8, or this negative 8 came from a factor with a power of 1, which is odd, so it switched over that. But this negative 1, that came from a factor with a power of 2, so what was on the left stayed same on the right. Everything else also came from a power of 1. So we switched when we went over the 4, and we switched when we went over the 9. So that's kind of our shortcut method. So here we go. Something like this. I'm going to make my number line, which is going to involve negative 1 and 3. Those are the zeros of the function f of x. And there's going to be values that happen. So something super negative like negative a million, that's the right number of zeros. That would make x plus 1 negative, and to the power of 3, that's still negative. And then x minus 3, well, who cares what x minus 3 is? It's to the power of 4, so it's never going to be negative. That's just always positive. So this, as its initial start, is negative. That's how we kick things off there. To finish it off, we say we're going to go over this negative 1. Do we change or do we stay same? Well, the negative 1 comes from a factor with a power of 3. And since that is odd, we will switch. And then as we go over the 3, do we switch or do we stay same? Well, that 3 comes from a factor with a power of 4, and 4 is even, so it stays same. And there's the diagram for f of x in example D. Take another, 7 minutes. Whoa, that's so odd. But try the other example, see what you get, and you can compare it to what happens when you do test values as well. But try the fast method first. Try kind of shortcutting it by saying same, or different. And then after you get that, and compare it to those around you perhaps, but try the test values method to see if your answer is actually correct. It's a great way to verify. And if you want, you can always fire up Desmos, because why not fire up Desmos? You can plug in your function, which says, whoopsie daisies, x plus 1 cubed times x minus 3 to the power of 4. Whoa, that's a crazy function. We can see on this left side, I don't have a pointer ability, but on the left of negative 1, it's negative. I'm in big mode. And then it crosses the x-axis at negative 1, goes way up high. Whoa. Okay, let's zoom out here. This is ridiculous. Way up high before coming back down. Touches the x-axis again at what we hope is 3. Let's zoom in there. Yep, that's 3. And instead of crossing, bounces back and becomes positive again. So there's the vibe of that particular graph. So you can check it out, see what happens. But again, try these other examples, and pause and all that jazz, and see you in 7 minutes. Whoa, has it been 7 minutes already? That went by wicked fast. Let's check out some sign diagrams. Example G. We've got some critical values. One of them is -7. The other one is 2/3. And we know those are associated with zeros for g of x. In this particular one, testing a seed value of -10. -10 would make x plus 7 negative. And it would make this something, but because of that power of 2, we know that's positive. And then there's this sneaky little negative in front, which is also negative. So we've got 2 negative factors and 1 positive factor. Overall, that makes this positive in the beginning. Then, as we pass -7, it will switch because that factor has an exponent of 1. And as we pass over 2/3, it will stay same because that factor comes from something with a power of 2. And that's that one. DUN, done. To the next. We got f of x and x. We've got 3 zeros here. -1, 0, and 1. And again, they all cause the function to have a value of 0. If x is -1,000,000, well, this thing's positive regardless. -1,000,000 plus 1 is negative. -1,000,000 minus 1 is also negative. So this starts out positive. It will switch as we cross over -1 because of the exponent on the associated factor. It will stay the same over 0 because of the exponent on the associated factor. And it will switch as we cross over 1 because of the exponent on the associated factor. And there is that sign diagram. Done. How many more of these are there? Like 100? Oh, just 2. That's not so bad. Whoa! The exponents on here are getting out of control. Who even made these things? They're wild. But let's see what we got. Big ol' number line that can fit all of these critical values. There's like 4 of them. So one of them's, let's just list them so I can keep track of what goes in what order. That gives us a 0, a -2, a -3, and an 8. All right, so lowest is -3, -2, a 0, and an 8. Those are all zeros of the function f of x. At the very beginning, -1,000,000 means, -2 times -1,000,000 will be positive. This thing to the power of 4 will always be positive. Same, this thing to the power of 4 always positive. -1,000,000 plus 3 is negative. That to the power of 5 is negative. So very beginning, this is negative. Ooh, that took a while. Hopefully I have a shortcut for the rest. And I do. This -3 comes from a factor with a power of 5, odd, so switches. This -2 comes from a factor with a power of 4, that's even, so it stays same. This 0 comes from a factor with a power of 1, so that's odd, that switches. And the 8, that comes from a factor with a power of 10, so that stays same on either side. Whew. Lastest one. What are my critical values here? Doodaloo. Oh, this thing would give us a 4. And this thing would give us a -9. And then this thing, I don't know, would it be like -1? No, it's not. You see, x squared minus 1 is more than x squared. If you think of it from transformations, you take your graph of x squared, and hey, and you move it up 1. So that thing is never 0. The graph of y equals x squared plus 1 does not have any x-intercepts. So that does not cause any critical values. Our only critical values here are -9 and 4. Those are all zeros of the function h of x. So this thing, I mean, from a graphical perspective, we know x squared plus 1 is always positive. We don't worry about that. And x minus 4 squared, as long as we're not at 4 itself, that's going to be positive. It's really just this x minus 9 that could change anything. And if we plug in something in this zone, like negative 450,000, negative 450,000 plus 9 is negative, making that whole region negative. We switch over the negative 9. We stay same over the 4. And then that one is done. Suggested practice, probably the worksheets? I'm pretty sure that's a good idea. I don't know. Athide says that's a great idea. With purple hair? So I'd work on that. If you have questions, you should find answers to them. You can message me or something, see what's going on. And that's about that. Play around with the practice work, of course. And again, graph things in Desmos and just see what they look like. Get a vibe for what's going on, where it's positive, where it's negative. And remember, like we're talking about y values there. And don't forget to stay awesome and give yourself a high five. The end. Hold on, stop this thing. Where's record it? Stop recording, I says. Stop now.